Claude, share screen. All right, so let's look at this. All right, so okay, so now you understand, you know, these indicators are actually showing different aspects that we care. And if this is very specific for certain purpose, we use a precision recall rate, especially recall rate. It shows that when certain thing happens, when the thing of interest, when the thing I care about happens, what is chance that my model can capture that? Okay, so that's recall rate. Accuracy is more neutral, showing that no matter what things is predicting, the likelihood it can give you the right result. And precision is only for the thing that I care about, the likelihood I can give a right result. Make sense? So let's do another exercise. This is a real example. And they were using, this is a nuclear plant, and they were using this camera to predict to predict if this person, this worker is approaching 1, 2, 3 different stations. Okay, so now the thing can be person A, approaching station 1, person A approaching station 2, or person B is approaching station 1, things like that. Okay, you got that. This is a computer vision machine learning model to predict the events. Now, let's say, what is the recall rate for this particular model? What is the precision for this particular model? This is, since this is time series model, so it's actually let's say this is time. All right, so this is time, and it shows that a continuous event, and this upper one shows the ground truth. Means from time point 1 to time point 2, this person actually approached station 1, so that's ground truth. And the blue one shows the prediction. Like from time 3 to time 4, this one predicted that person A approached station 1. Now let's say, what is the recall rate? What's the formula of recall rate? Can you guys give it a try? Anybody? Come on, anybody? Can you give a formula of that? Let's see, what should be the denominator? What goes above? Recall rate means I focus on the thing I'm interested in. This event, the event I'm interested in is person A approaching station 1. Okay, and the recall rate means when this thing actually happens, the likelihood my model can capture that. Make sense? So let's see, what is the duration that this thing actually happens? Anybody?
The positive.
It's which one minus which one? It should be T2 minus T1, right? Because this is this event actually happened. This is ground truth. Make sense? Yes. So this is T2 minus T1. All right. Then which portion of my prediction captures that? And it captures that correctly. Anybody? Let's say, is that T4 minus T3? No, because I know this portion is what? Incorrect. So should be which portion is correct?
T3 minus T4.
T3 minus T4? No, that's a negative number. Should be what? This portion is what? T2 minus T3, right? Yeah. T2 minus T3. Make sense? So let's once again, recall shows you know, how much my model can capture the events that I care about. And this event is this. That's the ground truth. And this is the portion that my model captures that correctly. So it's from here to here. Okay? And then divided by from here to here. That is my recall rate. Okay? Now let's say precession. Now, how do we calculate the precession?
T2 minus T1.
Going above or down, T2 minus T1?
Above for...
No, precession is what? Still, I focus on this event, but I want to see how much I predicted correctly. So
I think the true positive should be in the denominator, the top.
Which denominator should be what?
The denominator should be the true positive.
2 plus 2?
No, T2 minus T1, I guess.
No, actually that's the ground. Oh my goodness.
I think that's T2 minus T3 over T4 minus T3.
Correct. Who said that? Junyi? Okay, so let's do that. T4 minus T3. That is what? That is all my prediction. All prediction of my interested event. Correct? So that's T4 minus T3. It's this area. But out of this area, which is the correct portion? Only the T2 minus T3. Make sense? So this one shows the precision, the quality of my model in terms of predicting a certain event. Make sense? So let me review the answer. You guys can see the answer now? Okay, so once again, recall rate, I compare my model over ground truth. The ground truth is T2 minus T1 and shows that I successfully recall the portion from T2 to T3, which means I missed the portion T1 to T3, and I mistakenly predict the portion T2 to T4, but at least I correctly capture the portion T3 to T2. Make sense? So the ground truth is T2, T1, this part, but this is the correct part I captured. Precision focus on the accuracy of my model for this particular event. So this is the particular event. I predicted T3 to T4, but in fact, out of this portion, only the T3 to T2, this part is correct. So that's called precession. Make sense, guys? Okay, so pay attention to this, recall rate, precession. You might see some kind of, coordination system and, give you the T1, T2, T3, T4, and ask you to finish the formula for recall rate for precession. Okay, so this is a confusion matrix, 2 types of arrow, TP, true positive, true negative, false positive, false negative, and how we infer the 3 main, indicators. But the thing is, do we have a comprehensive index then, using so many index? The answer is yes. This is something called ROC and AUC. ROC is called Receiver Operating Characteristic Curve. Once again, this is very popular in computer science to evaluate their machine learning model. So it's very simple concept. We plot a graph first. X is the false positive rate. So here, false positive rate. So I get a number and I plot all the numbers here. And Y is the true positive rate. So why it's changing? Because you are changing your model. Imagine that you have this machine learning model, this neural network model. You change the values, you change the parameters. What will happen? The prediction result will be different, will be changing, right? So we try to change different, you know, parameters, we will get a set of a false positive rate out of all my predictions. And I will get a set of a true positive rate out of my prediction. So I plot everything here. Now, here's the thing. Whenever I'm improving my false positive, I'm improving my true positive rate, I'm running a risk of also increasing my false positive rate. Make sense? I'm predicting this guy is infected by COVID-19. But whenever I'm trying to increase the true positive, which means I predict this to be infected by COVID-19, and I'm right. Meanwhile, at the same time, I'm also running a risk that my prediction is wrong. Make sense? You guys get the point, right? And if a model is really bad, then whenever I'm improving my correct positive prediction, the likelihood that I'm making wrong positive prediction will be linearly increasing. Make sense? So this one becomes the random classifier or a random model, the voiced model. A best model is, you know, I'm increasing my true positive prediction, but then my false positive prediction does not increase at all. So it's kind of like, you know, I'm always in this line showing that I predict this person got infected by COVID-19. I'm always correct when I make this positive prediction. So there's no way for me to commit any wrong prediction. So this is the perfect model. Then for any model, they are sitting in between. You guys understand that? So we hope our model can be going closer to this perfect line and go away from this random line. So let's say if this is the line, here. Let's say if a line goes here, what that mean? That means for a given true, you know, positive rate, the likelihood for me to run this false positive is much lower than this line of running positive, false positive rate. You get my point? So let me just redraw it again. You guys are quiet, so I don't know, you know, if you understand my point. So let's say this is true, which is correct prediction of a positive event, and this is false, means it's wrong of the same positive event. And this curve and this curve, this model and this model, which model is better? Let's just plot the line from this. Let's say I desire to achieve 80% true positive, and I go from here. I found if I change my model to achieve about 0.8 true positive rate, then for this model, I have a chance of running about 0.38 false positive. Right? So I change my model. When I improve this true positive, I'm also running a bigger risk of running wrong positive prediction, but it's running about this level. But if I go from here and go all the way to check the orange model, the likelihood is become 0.7, which means I change my model until I achieve about 80% true positive prediction. Unfortunately, the risk for false positive also increased to 0.7. Make sense? So I want my model to be going further away from this 45-degree line. You guys understand that? Then how do I quantify how far I'm away from this 45-degree line? I calculate the area size covered under this line. This is called AUC. Make sense? So let me just erase that. So the AUC for this blue curve is this. Make sense? And the AUC for the green curve is what? Is this. So the blue curve AUC is bigger than the green curve AUC. Make sense? So AUC, once again, ROC and AUC, that's all very popular indicator in machine learning. So if you check machine learning papers, you will see, oh, the AUC of my model is this, the ROC of my model, AUC of my model is this, the recall rate of my model is this. It's all because of, you know, This is all how they calculate everything. Make sense? All right. This is the last thing I want to cover today. And this is another indicator to show the performance of machine learning model. Okay. So like I mentioned, we have the true positive, false positive, and my goal is to make this part as big as possible, right? But and also shrink the false part. But there's also a trade-off. Like, if I want to make this one bigger, I either need to, have this one bigger or have this one bigger. Make sense? I want my true positive to be bigger, but a side effects is I have to increase false negative or false positive. Make sense? So what is the best strategy for a model? Let's say a machine learning model to predict the likelihood of COVID-19 infection. We say we don't desire which one, false positive or false negative. We don't desire this one. Make sense? So then we want to have a model for this kind of a machine learning, application. And what's this model? This is a high recall rate or low recall rate. This is a high recall rate. Makes sense? So if I shrink this false negative, then I'm running my recall rate calculation is this one divided by this one. It shows that my recall rate is bigger. It makes sense. In order to use a machine learning model to predict a person got infected by COVID-19 nowadays, when this person actually got infected, the likelihood that I can capture that effect. And it's another way to say I want to reduce the false negative or type 2 error. Make sense? But a machine learning model to predict unsafe behavior of a construction worker, which situation we did there? This situation. Remember that? So this one means, I want to shrink the size of false positive. And coincidentally, this is the calculation for precession. So for this one, we don't want to have a good recall model. We want to have a good precession machine learning model to predict if this person, wears this hard hat or not. So in other way, in English, it means how the likely that I can correctly predict this construction worker wear a hard hat, right? So this is the one. Now let's say a machine learning model to predict sudden drop of stock price. Okay, let me just erase this one. Which is the desired situation if we run a machine learning model to predict sudden drop of stock price?
I guess low precision.
Low precision, high recall rate. Why? This is related to risk, right? So whenever the sudden drop happens, I want to make sure I can correctly capture that. So I want to correctly capture the sudden drop of the price. I desire a high recall rate, or I want the type 2 or false negative one to be smaller. But when I want to predict the sudden increase of the stock price, I want my model to be precise instead of the local rate. I know this is very abstract, but hopefully by reviewing the note and also the video today, you can get the sense. What I want to say is machine learning literature, computer science, they don't use accuracy to evaluate their model performance. It's 2 decades, 3 decades ago. So nowadays they use recall rate, precision, AUC, ROC, as well this very new score. It's called F1 score. You see, they want to find the balance between precision and the recall rate because this is real data. They found the model is not a deterministic. You can always fine-tune the model, change the model. But whenever you are increasing the recall rate, you are sacrificing the precision. Whenever you are increasing the precision, you are sacrificing the recall rate. You got the point? So it's kind of like a, orange and apples. You have to pick one. And they're so tired of it. They say, let's find a balanced one called F1 score. It's a formula arbitrarily decided by somebody. It's just the precision times recall divided by precision times recall times 2. It's called F1 score. The bigger, the more balanced the model is. It's probably somewhere here. And this is another new indicator to show that. Make sense? Okay, once again, guys, since this is important, let's just quickly go over this. First, let's forget accuracy. This is the old indicator to evaluate the machine learning model. So they actually use this something called confusion matrix to evaluate their model. And we are calculating 4 numbers, and the 4 numbers represent true positive, true negative, that's the correct predictions, false positive and false negative, that's 2 arrows, type 1 arrow, type 2 arrow. And which type of arrow is more dangerous? It all depends, right? And then based on the 4 numbers, we infer 3 main indicators: precision, recall rate, and accuracy. The accuracy is this one plus this one divided by the entire array size. So this one and this one means I made the right prediction, even though I don't have a focus of the prediction, but I made the right prediction. This is the most neutral prediction. The recall rate means I focus on certain event. This is purpose why I run this machine learning model. And I want to see when this event actually happens, the likelihood I can capture that. So this is called a recall rate. So I use this one divided by these 2. But precision is also focused on the specific purpose of my machine learning model. I just want to see when I predicted this thing happens, the likelihood that I'm actually right. So I use this one divided by this 2. Make sense? But once again, this is still purpose-specific, general use. Make sense? And this is example like how we identify the 4 numbers and how we calculate precision, recall, and accuracy. This is another one, right? So this is the true event I focus on. I want to see when this thing actually happens, the likelihood I can correctly capture that is here. So then this one divided by this one is my recall rate, right? And then when I predict this thing happens, the likelihood that I'm actually correct is only this part. So using this part divided by this part, that's precision. Make sense? Okay, and then the computer science guy say, hey, I want just one number to show things around. This is called AUC. I basically just say whenever I'm increasing my true positive prediction, I'm running a risk of also increasing my false positive prediction. And the worst model will go 45-degree line, and the best model will go 90-degree line, and the other models will go a line in between. And which model is better? You just go from the one I did there and draw a line and see the risk associated with the false positive. Oh, the line that closer to the 90-degree line is better. So then we calculate area size covered by this line. We call this AUC. Okay, and they also figured out for different purpose, we do desire a smaller false negative or a smaller false negative or smaller false positive. It means that the recall rate is bigger or the precision is bigger. So depending on the function, depending on the desired purpose, I could pursuing a high recall rate model or high precision model. And how to find the balance, they discover that whenever you are increasing the recall rate of your model, you are also you are sacrificing the precision of your model. So in order to find a balance, they develop a new indicator called F1 score. Is this times this divided by the summation of them times 2, and it's trying to find the balance of them. Make sense, guys? So that's the model evaluation. All right, so let's take a 18-minute break. Let's return at 6:30. I'm going to show you some cool stuff then. All right. See you guys then.